Good afternoon to all. Good afternoon to all. It's our Professor in Institute of Technology, Patna. Sir, it's an honor to have you here. I welcome you formally for this conference. Part of the interactive lecture series, Bihar's Population Control has not This topic is Metallurgical Recovery of Metals from E-waste for the circular economy and challenges and opportunities. We all know that e-waste is a growing concern for all the stakeholders in the country, not only in the country, throughout the world. The growing economy, the electronic and electrical equipment keep on increasing. At the same time, with the pace of new innovation, a lot of electronic items are becoming obsolete, and that requires a proper disposal facility onto e-waste to reduce or to have least impact on the environment and public health. We as citizens use a lot of electronic and electrical equipments in our daily life. So this is a very pertinent topic also for today's discussion. So with this view, I request Mr. Arun Kumar ji to introduce today's honorable guest speaker to the audience. It's over to you, Arun. Thank you, sir.
Thank you, sir. We have a privilege to here. We welcome Dr. Subrat Hait in this meeting. He is a economic researcher and currently working as associate professor in the Department of Civil and Environmental Engineering at Indian Institute of Technology, Patna, Bihar. He obtained his PhD degree in civil engineering for the research for metal growth membrane bioreactor for sewage treatment coupled with the vertical composting of sludges from IIT Patna in the year 2000. Prior to join as an associate professor at IIT Patna in 2012, he worked as a senior project engineer at IIT Patna within a consortium of 7 IITs for the Ganga River Basin Environment Management Plan, GRB EMP, a project sponsored by the Ministry of Environment, Forest and Climate Change, Government of India, for abatement of pollution and creation of continuous and unpolluted flow of the Ganga River. He also served as the head of Department of Civil Engineering for 3 years from 2016 to 2019. He is a fellow of Institution of Engineers India in the Environmental Division and affiliated to the organization like the American Society of Civil Engineers, International Solid Waste Association, International Water Association. Apart from serving as the reviewer of for different international journals published by the leading professors, including Elsevier, Dr. Hait is serving as an academic editor of two PLOs, one and PLO's Water, and an editorial board member of Asian and Science, Springer Nature. So we have a great opportunity to have Hait with us.
I request Saha, senior colleague, you were about today's topic. Over to you.
Thank you, sir. As our secretary has told, all our stakeholders is particular based on it. We all are just, we all are consumer first, users also, and generator also. These are where we all are covered. Really, recycle these wasting out of economy. Wealth is being wasted into our atmosphere, which is ultimately on our environmental sustainability. So, in this topic, how this can be of certain economy, and how much is we'll have a links and we'll have an estimate, we'll have an inventory across the world also, and we'll have our India also. And we should regularly give us some motivational information and we can participate in this program for the recovery of this waste and wealth of our environment. Thank you very much.
Good afternoon, everyone. Thank you very much. Just a person for initiating this lecture interactive series and inviting me to deliver the second lecture in the series. Thank you very much. Other present here in this room, and also the audience. Can I have a slide? In this lecture series, second lecture, I'll talk about metallurgical recovery of metals from challenges, opportunities. In day-to-day life, lot of electrical and electronic. All along the years, we have talked about a lot about the solid waste, wastewater. But we talk about the electronic waste or the EO. Okay. So let us first look at what is EO. Before that, what it has is in our day-to-day life, electrical and electronic. What are those electrical and electronic? Have you ever wondered what happens once they are getting obsolete? What we need to do with them? So, how electronic gadget or devices which current or electrical and electronic they become obsolete. And this can be the information telecommunication equipment, see, or these electrical electronic equipment have refrigerator. These ones is electrical electronic. They over the years they become obsolete. Not have any use to us. Right? They get converted or manage waste electronic waste or manage e-waste. Now, why is taking place? Over the years we have rapid technological advancement and this electric there comes a lot of advanced features. Fine. Whatever the typical age of the date was there, that is actually because of the rapid technological advances. So more and more waste, electrical and electronic waste is very more. Now, how we need to deal with this? First, let's look at the global US generation. The global US generation currently, the US generation in 2019 6 million metric ton mine, and it's now 5,400 of like, by now you can imagine how much world we are generating the electronic waste. At the opinion wise, see that China is the least around 10 million metric ton, followed by US. India is the third in the world. This 50.6 million metric ton, which is 40%. So roughly around a year, you can think about. I'm sure you know about this medal. The last Olympic, the Summer Olympic was most 2021. 2020 medal was essentially about was the medal made out of project was essentially of collection of US from 79 kiloton of US, the mobile phones collected from period of till 2017. From this electronic waste recycled made around 8,000. If you look at the average obsolescence stage, the typical obsolescence stage of the various electrical, okay, and there you can see the computer typically the average obsolescence stage is 3 to 5 years. At the laptop, which is all let us say about the consumer electrical electronics which are mentioned, each refrigerator or washing machine or they are 9 to 10. These are typical obsolescence stage. Because of this obsolescence stage or this is very so more than so we need to think about this now we will discuss at the end. Okay, so now this system of US generation further compounded by country. Yeah, despite the Basel 1992 prohibits this term of the find the developing countries, China, have become US graveyard. So essentially, from the US, from the North America, or Western, have become countries. Thereby, this had further compounded our now let us look at national status. So we have a timeline starting from 2019. 2005, CBCB estimate is saying that 1 million metric tons, and over the years by different organizations, in CBCB also in 2012 was 8 billion metric tons of generated. The latest estimate by the United Nations said that India generated 3.2 billion US and we are rated among the third highest in the world. Now, with this used instance, then again this is the conservative estimate. Once we have this generation statewide. In terms of percentage, in India, start with around 20% of minerals, followed by Andhra Pradesh, and so on. But uh, estimate this will count around 1.15 or 2 million metric ton. So what is USD generated in India? They are essentially. So essentially, if you look at the right side chart, but you can see that only around 20%. Whereas big percent of POS now, if you look at further, as with this recycling, total around 472 of data, 472 are for the recycling units, total capacity of 1 fine, and 2009 it said that we generated fine different recycler, and they are essentially around 20. Fine. This informal recycling sector project okay.
Right.
If you look at the informal USD recycling in India, these informal USD recycling sites are mostly situated in Delhi NCR, where we have cheap labor and using the imported facilities, we have a lot of sites of these recycling units. They use typically the inventory or limited technology. See there. Last 40 have efficiency of these and you know waste and people make okay, but as techniques. Let's talk about US region. So first I will talk about global view of US region. All over the world, see, first of the US started way back in 1990. They, Switzerland, Japan, US, in India, we have started focusing on area or developing system. And US 2016 of that earlier 2016. Then this group was marked up, amended in 2018. Right now, it's known as US management. Okay. These whatever the second features I will mention, I will not go to the next part. Already dealing with. Are and this is the responsibility of India plan in year 10% of collection of UAS for each producer. 10% 70% producer. So target approach we can implement. Yeah. Also, we have now as producers. Fine. So if you look at the chain, what you have is essentially the producers. Fine. Producers have the dealer or you have the retailer. Some e-retailers are also producers. Fine. Now let me clear that the e-retailers are those which exist in part of it, yeah, including internet or the telecom network through which or seeing this the electrical and electronic equipment. So these like say e-retailers nowadays are very common, you know, the Flipkart, Amazon, or eBay. So these e-retailers are also now considered to be as producers. Then followed by what you have is the pan-India EPR authorizations of the producers, fine. And you have the collection is now responsibility of the producers, and producers are mandated to have a PRO for what is mentioned as producer responsibility organization. So you have the producers, the dealers, retailers or e-retailers. So you have, and then it is going to the consumers. So in the consumers, once they use, so here I want to mention that consumer, apart from the consumer, you will also have individual consumers, or you can have also the bulk consumers. Bulk consumers are like, let us say, any government or semi-government organizations or school, colleges, or public sector units, okay, or the banks. So they generally consume or utilize this electrical and electronic equipment in bulk amount. So that's why they are known as bulk consumer. So you have a consumer, or you will also have a bulk consumer. Fine. So followed by this, you will have this. Once they are getting obsolete. So now it is the responsibility of the producers or the PRO to collect it under various schemes. You have now the take back system. So when you purchase a new mobile phone or an electronic gadget through let us say e-retailers, nowadays they ask for, if you have any old item, you can give it back to them, and you need to mention some kind of that what is the condition of those products. Fine. And thereby they will provide some kind of scrap value. Fine. So that what is, you have the take back system, or the producers or the producer responsible organization PROs, they are also mandated to have the collection centers. Fine. Apart from that, the producers also have some kind of a refund deposit scheme, okay, through which during the sale of any product, they keep some kind of extra amount or extra money when they sell any kind of electrical or electronic equipment. Fine. And thereby once the product is getting obsolete and you return it to the seller or the producers, they will give you in return that whatever, or they will refund that amount with interest. Okay. So that what is meant to is this refund scheme. So through these various schemes, what you have is that collection and channelizations of e-waste is done to what is known as authorized recyclers or the dismantlers. And this what I am talking about is the formal sectors. Okay. Once they are done in this, what you have, if they are environmentally sound techniques, and this we will talk about later in this lecture. Once they are the recycling is done, that whatever material is generated generally can go to the material market. And overall, everything is done or supervised or regulated by what is known as, you have the Central Pollution Control Board as the authorizations, and monitoring regulatory agencies are the state pollution control boards in the states, or you will have pollution control center in the union territories. Okay. So based on this, what you have is the collections producer responsibility with no separate authorizations. Now also, like we pay, like we need to file the income tax return. Similarly, the bulk consumers now need to file annual return with respect to the e-waste generation and how much is e-waste generated. Okay. Only exemption is provided to the micro enterprises, which is defined in the MSME Act. Okay. Now, in various electrical and electronic equipment has been mentioned under the schedule 1 of these rules. Fine. So there, whatever the equipments earlier was included. Apart from that, the compact fluorescent lamp and other mercury containing lamps are also brought under the purview of these rules. So they are also now considered to be as e-waste. So as I have mentioned, it's essentially the stakeholders in this entire framework is essentially you have the generator, which you have the consumer and the bulk consumers. And then you have the e-waste handlers and the processors, which will have producers, or you will have the producer responsibility organizations PRO through EPR. And then you will have, and I have already mentioned that producers are also consisting of dealer, retailer, and e-retailer. Okay. And then you will have, let us say, recycler and dismantlers, they will come under this e-waste handler and the processor chain. And then you will have the regulatory bodies I have mentioned, the Central Pollution Control Board or State Pollution Control Board or the pollution control centers in the union territories. Now let us say introduce the circular economy or the C or e-waste as a tool. Fine. Now, so far what we are doing is essentially we getting a lot of natural resources. So that what we are making is a tech. Then we are making this product, the electrical electronic equipment, and then we are using it and then dispose it. Fine. So what you have is now is take, make, use, and dispose model. Fine. Now the circular economy, what it does is essentially a regenerative economic system, which is transitioning from this take, make, use, dispose model to what you have is take, make, use, and regenerate resource model. Fine. And thereby what you have is that the e-waste, which earlier used to be thrown away or disposed improperly or unscientifically, fine, and thereby what you have is lot of wastage of resource and wastage of economic values, and also you have the environmental pollution as well. Fine. So from transition from this take, make, use, dispose model to take, make, use, regenerated resource model, by doing this, what we have is now which can have sustained economic growth, we can have environmental protection, and also it will lead to a lot of job creation, and then it will lead to the societal well-being. Fine. And this is in line with whatever the sustainable development goals we have, which we need to fulfill by 2030. Fine. Now this circular economy model, what we have is typically 6R principle for any waste, and for also for, let us say, for e-waste management. What we need to have is the reduce, reuse, repair, refurbish, remanufacture, and recycle. So these are the 6R principle what you have. So here what we mean to say is refurbishing. Okay, refurbishing or repair. Essentially, if you have a electrical and electronic equipment which are in use, okay, you take it to the repairing shop, okay, so that you refurbish it, so that you can the working life of the product is getting increased, and then you reuse it or sell it in the open market. So that's what is known as the refurbishing or this is a particular typical type of repair. Fine. So essentially, if you introduce circular economy here in the e-waste management, you can see that you will have recyclability option, and thereby you can have resource recovery. So far, what we are essentially wasting them. Fine. And these C principles are essentially integrated in whatever the legislation we have, whatever we mentioned as Indian e-waste management rules, whether you look at the 2016 or 2018 amendment rules. Now let us look at with respect to e-waste composition. Fine. If you look at e-waste as an overall stream, you will see we have typically around 37% of the glass and 30% of the plastic. And we know the glass has typical recycling route, so as also the plastic. So we will not essentially focus on the glass and plastic here in this talk. Fine. But we focus, as the title says, is we essentially focus on this metallic part. Okay. And when you talk about metals in e-waste, you can look at mostly you will have iron, copper, aluminum, and zinc and lead. Fine. Although I am saying here these are the metals which are the most prevalent in terms of weight percentage. Apart from that, what is most importantly, we have a lot of precious metals. You can think of silver, gold, platinum. They are also present in substantial amount. Apart from that, we have a lot of rare earth elements, which are not typically focusing in US stream. These rare earth elements are essentially pivotal for development any new technology in electrical and electronic equipment section or the sector. Fine. Now, these rare earth elements, a typical source is the ores in the mining. Fine. Now, these mines are monopolistically controlled by few countries. Fine, including China. Fine. So now the China, what has done that they have stopped exporting these rare earth elements. Fine. This is one aspect. Another aspect is these rare earth elements, which is their extraction from the ores are also very cumbersome. Fine. So looking at them, then what is the way out for any other country? Because you do not get rare earth element, then whatever program you have, let us say Make in India and all these things will ultimately suffer. So what we need to have is that to get all these elements or the metals from the this EOS stream. Fine. Now, when you look at this EOS, the core element, what you have, as you can see here, is the printed circuit board. This printed circuit board is the core component or the integral component of any EOS or any electrical electronic equipment. Now, to look at the printed circuit board composition wise, they are typically what you have is they have the base of each essentially the plastic and polymers, which is having 30%, glass and ceramics, you have 28%. Fine. And within this base, what you have is these metals are embedded. Some are in the mounted component, or some are in this platform in the base. Fine. So our job as a research community is to extract those metals, including the general elements or the precious metals or the rare earth metals from the complex matrix, so that we can reuse these metals and integrate this circular economy approach. Fine. So based on this, what you have typically, I can show you. This is from our laboratory in IIT Patna, which we are doing in the pollution prevention and resource recovery laboratory. So there you can see we have this typical end of life computer printed circuit board, as you can see. And the printed circuit board, you can see there are a lot of mounted components. Fine. Apart from this base material or the platform. Fine. So this mounted component, you can see, you can name any element they are present. Whether you look at capacitor, you look at resistors, you look at the solders. Fine. Now in this, apart from these mounted components, you can have in this base or the frame, you have a lot of metals as well. Fine. The people will understand why we are using, let us say, gold, silver here. Fine. So gold, silver is typically used as soldering material, apart from, let us say, lead and tin. Fine. Also, we need to provide some kind of thin film over this. So thin film is essentially of gold and silver, so that you can protect from the corrosive environment all these metals which are embedded here. Otherwise, these electrical signal pathways will get corroded over the years. So thin film is provided, thin film of gold and silver is provided. Fine. So this is one example. Similarly, you can have, this is a typical printed circuit board of smartphone. And as you can see, also the mounted components, you name any mounted component, you will see a lot of the metals are present here, including precious metals and the rare earth metals. Similarly, this slide is not working. Yeah. So similarly, you can see this is a typical printed circuit board of cathode ray tube. Earlier, we used to have a bigger tubes. So this is a cathode ray tube television. I'm not talking about the smart TVs. Okay. So this is the typical CRT TV's printed circuit board, and this is a bigger one. And also you can see here a lot of mounted components apart from this, the platform or the base. Fine. So everywhere you can see whether mounted component or this, you have this, the metals are present. So our job from these, the complex, from this complex platform, we need to extract these metals so that we can reuse them again in manufacturing of electrical electronic equipment, so that this integration of circular economy approach can be done. Now, since we are talking about recycling technique, used recycling technique, or particularly, let us say, since we are focusing on printed circuit board, the printed circuit board, the metal extraction of techniques or the metallurgical techniques are essentially three. One is what you have is the pyrometallurgy. As the name suggests, we provide in the pyrometallurgy, which essentially provides some kind of heat treatment. At elevated temperature as high as 3000 degrees centigrade, we generally heat this the printed circuit board. But remember, this printed circuit board, what you have is their base is essentially the plastic or the polymers. So if you burn plastics, as you know, this can generate a lot of air pollutants, including, let us say, dioxins and the furans, which are typically carcinogenic in nature. Fine. Although pyrometallurgy is efficient in terms of metal extraction, but they suffer from the secondary pollutions of having air pollutants. Okay. Then what you have is a second technique, what is known as hydrometallurgy, and which is also known as the chemical leaching technique. So printed circuit boards are subjected to chemical treatment. What kind of chemicals do you use? Typically, we use, let us say, strong acids or strong alkali. What are the strong acids? Let us say any kind of mineralized acid. The mineralized acid could be, let us say, sulfuric acid, or it could be hydrochloric acid or nitric acid. Once you extract the metals, which is fine, okay, efficiency wise also very high, fine. But what about the waste generated from the hydrometallurgy? Because you have a lot of, since you are using a lot of mineralized acid, so the wastewater what is produced, you need to properly treat them, otherwise you cannot dispose them into the environment. So also a lot of hazardous wastewater is getting generated in the hydrometallurgy or chemical leaching, typically using mineralized acid. And thereby this is also creating secondary pollution, despite this process is also being efficient. The third technology, metallurgical techniques, what you have is known as biometallurgy techniques or bioleaching. As the name suggests, is bio. So we are using some kind of biological entity, microorganism. This microorganism could be bacteria, this microorganism could be fungi, or their product. Fine. So it could be any kind of microorganism, or this could be any kind of product generated from the this kind of biological entity. So this process, biometallurgy or bioleaching, they are eco-friendly, efficient. They do not create any kind of secondary pollutions, but they are essentially a slow process. Since we are employing microorganisms, they are essentially a slow process. Okay. So if you look at this advantage and disadvantage I have mentioned here, if you look at the environmental impacts point of view, and this signifies the red one is the extensive, the blue one is the fair, and the yellow one is the low. So if you look at pyrometallurgy, the hazardous gaseous emissions will be very high in case of pyrometallurgy, because you are burning the plastic, because the PCB matrix is essentially plastic. Then it will have fair amount and least amount you will get in the biometallurgy with respect to gaseous generation. With respect to wastewater generation, you can see extensive wastewater is generated in the hydrometallurgy, which could be corrosive in nature or hazardous in nature. And then least amount is pyrometallurgy, and some amount can be also generated in the biometallurgy. But biometallurgy technique, they are essentially biodegradable. Fine. So based on this, you will have compatibility with the environment. So here, high compatibility with respect to biometallurgy, fine, and then followed by you will have hydrometallurgy, and then you will have pyrometallurgy. Fine. The least compatible, what you are saying with respect to the environmental component, is the pyrometallurgy. Similarly, how much is investment required? With respect to the investment required will be very high in pyrometallurgy, followed by hydrometallurgy, and least will be essentially biometallurgy. Similarly, we provided energy consumption. Since we need to burn the waste, we will have high energy requirement in pyrometallurgy, followed by hydrometallurgy, and then we will have in the biometallurgy. On the other hand, if you look at the time requirement will be least in case of pyrometallurgy, and then the hydrometallurgy and highest time will be required in biometallurgy, because we are essentially employing the microorganism. Fine. And if you look at all these metrics, the level of research, which we will talk about the latter part of the talk, the research wise, you will see the extensive research has been done in hydrometallurgy. Okay. And although the pyrometallurgy is an older technique, fair amount of research has been done. The least amount of research has been done because the biometallurgy is the emerging area. Fine. So based on this, what was our motivation to work? The motivation wise, if you look at the printed circuit board, this printed circuit board with respect to its structure, with respect to the manufacturing process, with respect to its compositions, they can be of various types. Fine. Now this printed circuit board of various electrical and electronic equipment, let us say you have a lot of electrical and electronic equipment, as I have mentioned, some are IT and telecommunication equipment, some are consumer electrical and electronic equipment, some are large household equipment. So our motivation to have whatever the printed circuit boards we are getting from various electrical and electronic equipment, how they are essentially in terms of composition, how they are different with respect to, because when you go for recycling or metal extraction of the US or the printed circuit board, first we need to know that how much metals or these valuable metals or other metals are present, and how this printed circuit board from different electrical electronic equipment or the products are varying. So this was one motivation. Second motivation was, let us say, if you do not environmentally sound way, if you do not dispose this electrical electronic equipment or recycle them, let us say you throw them electrical and electronic equipment once they are getting obsolete, that you throw them into the open environment and let us say in the with the solid waste stream. So if they are getting exposed to the environment, fine, and let us say you have sometimes they will come in contact with water, any surface water, groundwater, or let us say for you have acid rain, okay, and they are ultimately reach the surface water and the subsurface of the groundwater, and it will contaminate. Okay, so one is what we are saying key, if you unscientifically dispose them or recycle them, they will create environmental pollution, fine, and also there will be loss of resources and loss of economic loss as well. Okay, in the process, what we wanted to understand that how if you unscientifically dispose them or recycle them, what could be their toxicity on biota, toxicity to the environment, toxicity to the human being. Fine. So that was also our motivation with respect to the research efforts at IIT Patna. Then, with respect to technology development, as I have mentioned, the hydrometallurgy technique, they mostly use chemicals, and as I mentioned, the mineralized acid. But what our motivation was, we will not use any kind of mineralized acid, but what we will use is organic acids, which if you dispose them into the environment, they are essentially biodegradable, or if you can use some kind of biopolymers or the green chelators. So we will not use any kind of mineralized acid. So if you can use organic acid or the green chelators, fine. Then if you look at biometallurgy technique, we have mentioned biometallurgy or bioleaching technique, fine. In nature, microorganisms, they generally grow or work together in tandem, in symbiosis, fine. So mostly the studies have been done that you have pure culture of any particular type of bacteria. So can we have some kind of mixed culture of bacteria, various types of bacteria, which can have this extraction of metals from the printed circuit board, fine. So that we wanted to explore. And we wanted to explore, since biometallurgy technique or bioleaching technique suffers from, let's say, drawback of higher time requirement, can these two techniques be clubbed? Let us say you have chemical hydrometallurgical technique with the using of Sefar lixiviant or the Sefar organic acid or the green chelators, and along with this biometallurgy or bioleaching technique. And can we have some kind of technology development, which we call it as, let us say, hybrid technique or hybrid bioleaching technique. This is just one example that chemical leaching and bioleaching can be combined, fine. And thereby, if we can have process efficiency can be improved, as well as the time requirement can come down, fine. So with all these modifications, let us first look at the characterizations of printed circuit boards of various end-of-life electrical and electronic equipment before we go for their recycling effort. Fine. So here you can see almost 16 electrical and electronic equipment covering IT and telecommunication equipment, covering the consumer electrical and electronic equipment, covering large household equipment. So from each of those equipment, we have collected from 2 different brands printed circuit boards of 3 each. Fine. So you have a 16 electrical electronic equipments, 2 brands, and 3 printed circuit board each from each brand. Fine. And then what we have done is almost 33 elements we have characterized them. 33 elements, general elements, toxic elements, and then precious metals with respect to gold and silver. And also we have characterized them in terms of rare earth metals or the rare earth elements. And we have also noted down that if you have a typical electric and electronic equipment, how the printed circuit boards, they are varying in terms of their weightage. Fine. So in the methodology wise, we generally try to pulverize or crush them, and then we acid digest them in the microwave digester, and then we determine the metallic content in the ICP-MS. Fine. So based on this, what I have found out, and this we are talking about only in the printed circuit board. So copper was the most abundant metal in the printed circuit board. Earlier, what we have mentioned is essentially iron was the most in overall used. But if you look at the printed circuit board, copper is the most abundant metal present. Okay, and which is typically 1 to 23 weight percent. You can imagine how much is the value. Okay, and we have seen the highest content was in the laptop. Fine. Then lead, which is also can be considered to be as a toxic metals. Fine. They also present as high as 15 weight percent. Highest was there in the DVD player printed circuit board. Then if you look at aluminum and zinc, likewise, their content is given, and mostly they are either found in the computer and mobile phone. Now look at laptop, computer, and mobile phone. They are essentially IT and telecommunication equipment. Okay, these are IT telecommunication equipment. Their obsolescence age is very low, and increasingly that is coming down. Fine. So they are generating more and more e-waste. IT and telecommunication equipment is from that segment, we are getting a lot of e-waste generated. Now, if you look at also the toxic metal wise is we have mentioned about lead. Also, you can just look at the chromium. Fine, they are also present, and the TV remote control what you have in that as high as 220 gram per ton of chromium is also present. Now, interestingly, if you look at the precious metals, we have gold and silver. So gold, you can look at the highest was 316 gram per ton, again in the mobile phone, while the silver was highest in the laptop, around 636 gram per ton of printed circuit board. Fine. So a lot of precious metals are also present. Then if you look at the rare earth metals, which are critical for the development of electrical and electronic equipment. So rare earth element, the scandium was highest in the mobile phone, and cerium was present in the highest in the CFL. And so what we are saying, the general element, toxic metals, precious metals, rare earth metals, all are present. Some are very abundant quantity, or some what we are calling it as a substantial quantity can be recycled back. Fine. And if you look at their resource value wise, as we are saying, the resource value, because circular economy is essentially based on the with respect to the economic development. So you look at IT and telecommunication equipment will have major resource value or the most resource value as compared to the others. And this IT and telecommunication equipment, they will have a lot of e-waste generation because the rapid technological development in that sector, as well as their obsolescence age is coming down. Fine. Followed by you will have large household equipment, and then consumer equipment and the lighting equipment. Fine. So this is what we have, but before go for recycling, what we have done is the characterization of this printed circuit board. And as you can see, most of the printed circuit board, you have extensive resource value. Now, we wanted to also look at particularly a product, let us say mobile phone as a product, how their metal content had changed over the years. Fine. We have had basic phones, let us say in early 2000, and then let us say subsequently 2004 or 2005, we have smartphone. How their metal content had changed, and during that period also we have, or the beginning of that period, we have also a lot of international legislations have come. Let us say you will have a restriction of hazardous substances or use of restriction of the hazardous substances in the electrical and electronic equipment, and also we have had waste electrical and electronic equipment directive, and those are essentially in the European Union. Fine. So we wanted to look into that whether the in a particular segment in the electrical and electronic equipment, if that the manufacturer, the producers, they have mostly focused on their market profitability, or they have focused, let us say, with respect to environmental well-being or environmental protection. So that's why we have chosen mobile phone as a product, and how they have, with respect to their material compositions in terms of the metal, how they have evolved over the years. So we have collected around 16 from 2000 to 2016, we have collected mobile phones. Some are basic phones, some are smartphones, and what we have compared is with respect to liquid crystal display. We have compared the printed circuit board. We have compared the plastic housing. How is the metal content present? And also we have compared about the total content. Interestingly, you can see here, in the liquid crystal display, although there are international regulations prohibiting what you have is the use of these hazardous substances, the metal content, including some of the toxic metals, their content has tripled over the years. Starting from, let us say 2000, and in 2016, it has tripled. Fine. Printed circuit board, as you can see, their metal content remains almost similar. Okay. And interestingly, what I've seen, because of the regulations, the use of lead in the printed circuit board has come down. Fine. Also, the manufacturer, they are focusing on more on market profitability with lesser amount of use of the precious metals. Fine. And also with respect to their plastic housing. So as a whole, the metal composition, and we have substantial data from 2000 to 2016, we can safely say that the manufacturer of electrical and electronic equipment, particularly in this, let us say, the mobile phone sector, they have mostly focused on market profitability because of the rapid technological advancement, rather than looking at the environmental protection or environmental well-being. Then if you look at toxicity characterization, so if you dispose, let us say, these printed circuit board or the e-waste with the solid waste stream or in the openly in the environment, what you can see here is we have performed toxicity characterizations using standardized test and some of the modified test. So you have the printed circuit board from computer, laptop, washing machine, CRT television, and air conditioners, and they are being subjected to standardized test, let us say extraction procedure or TCLP. Suppose you dispose this e-waste of printed circuit board along with the solid waste in the landfill. What will happen? The metals of the printed circuit board present there, and how they will behave, how they will induce toxicity. Then suppose this e-waste or printed circuit board is subjected to acid rain. Fine. So how these metals or how the e-waste will behave in terms of the toxicity, or how they will induce toxicity. Or suppose these are subject, or they are come in contact with normal water, any surface water or groundwater, how they will behave. Fine. So based on this, the standardized technique of EPTCLP for landfill conditions, SPLP for acid rain conditions, ASTM, which is the American Society for Testing and Materials, with respect to the normal water or how they will behave. So these standardized tests were performed with respect to all these printed circuit board from the electrical and electronic equipment. Okay. So we also wanted to have this standardized test, particularly this SPLP, is developed considering the westernized condition. Because their acid rain was typically, the pH of the acid rain was 4.2. Now, how this acid rain pH varies in India? Okay, so what we look at, what is the typical pH of acid rain in Indian conditions? Because we cannot just simply copy whatever the methodology developed by the Western countries and then implement here. Right? So we wanted to look at if we change this, modify this procedure. Let us say looking at what is the acid rain condition or the pH of the acid rain condition in India. So we look for, let us say, last 15-20 years data of pH in the acid rain and whatever the designated stations all over the India. And what we see is that acid rain pH in Indian condition is typically 4.8. And then we perform this test. So what we have seen that if you subject this test or the standard procedure or the modified procedure, essentially lead and nickel they are crossing the toxicity limit, which is prescribed by the international agencies, and they are essentially present in substantial amount in simultaneously. So since they are crossing this threshold, particularly they can induce very severe toxicity, and that's why mostly this e-waste stream is considered to be as hazardous stream, fine, and we need to take them as hazardous waste. If you look at the technology development with respect to the circular economy approach, as you have mentioned, we have started with the hydrometallurgy or chemical leaching technique, but without adding any kind of mineralized acid. So what we have used first organic acid, which are biodegradable in nature, and they have some kind of chelating property, metal chelating property, because we want to recover or we want to extract metals, fine. So first we have started with the computer printed circuit board, and then we have as a pre-treatment, we generally grind them, fine, in milling operations. Then we have performed the experiment, and what we have seen, as you can see here, is typically the metal extraction efficiency can be as high as 97% or 99%. Fine. Only is that it requires, since we are using organic acid, the time requirement earlier, let us say if you use mineralized acid, if they can be achieved in let us say 4 or 5 hours, this is achievable in 4 or 5 days or 3 days time. Fine. And then what we have seen, once they are extracted, we need to recover because they are present in the solid form. Fine. By doing this chemical leaching using this TTPA, what we are bringing them into the liquid medium. Once they are in the liquid medium, we need to recover them, fine, in terms of, let us say, metal oxides. Fine. So one procedure what we have adopted, there are several procedures. One procedure is the selective chemical precipitation, through which, as you can see, once they are extracted, the extraction efficiency I provided 97% for copper, 99% greater than 99% for zinc and nickel. Fine. Then further, we have recovered them 98% of copper, 95% of zinc, and 98% of nickel from the extracted medium. So you can recover. And this is just not only we have performed in the laboratory as a batch study, we have a continuous operation in the column reactor. The batch study, what you have is a limited utilization of your electronic waste. So if you use column reactor, there you can use a lot of e-waste or a lot of printed circuit boards. So there we have got also the similar kind of result. So as compared to the mineralized acid, if you use this organic acid, DTPH organic acid, what we are getting similar kind of efficiency. Only trade-off what we need to do is the time requirement will be more. But here we generally do not have any kind of secondary pollution, because whatever the liquid is generated, they are essentially biodegradable in nature. If you throw them in the environment, they will be essentially, for the natural organism was present, they essentially will biodegrade them. Followed by this, we have also tried with another organic acid, let us say acetic acid, which is commonly used, and also we have used biopolymer. I'm sure you have heard about these chitosan, which are generally present in, let us say, the crust of the shrimp. Okay, so from that we can have this biopolymer, and they are also having chelating property. Fine. So here also we have performed computer printed circuit board, subjected to the milling operations, and using either acetic acid or this chitosan as biopolymer. Okay, so what we have got is using acetic acid, as you can see, 99% of copper, 99% of zinc, 85% of nickel, 82% of lead. Only problem is the 7 days time requirement. Using chitosan, you can also see similar kind of efficiency, but time requirement is 5 days. Followed by this extraction from the printed circuit board solid matrices, again we have recovered them using the chemical precipitation. The recovery is pretty high, as you can see, more than, let us say, 95%. Fine. So for all the targeted metals. So chemical leaching can be also utilized without creating secondary pollutions, and it can contribute to the circular economy. Only thing what you have is that we are not using here mineralized acid. Only problem here is that it requires comparatively higher time. So there has to be some kind of trade-off between your whether you want to harm environment or you want to have or safer environment. Followed by this, what we have had is biometallurgical technique or bioleaching technique. Fine. And there we have mentioned mostly in the research, they have essentially focused on individual species or a pure culture. So what we have done in our laboratory is we have taken computer printed circuit board, then we have provided pre-treatment. Now they are subjected to what? We have provided mixed bacterial strain. One is Acidothiobacillus peroxidans and another is the acidophyllum. Fine. And they can complement each other. This kind of microorganism we have chosen. Here, since microorganisms there, since printed circuit board doesn't provide any kind of food or substrate, we need to provide some kind of commercial medium. Fine. So that medium is 9K medium. So what we do is we use this pulverized printed circuit board, we add this culture and then 9K medium together. And what we have also done, we have varied the waste quantity as well. Let us see, you can see, and what is known as the pulp density or e-waste pulp density. And that pulp density is typically what you have varying from, let us say, 7.5 gram per liter up to 15 gram per liter. So whether we want to see if the efficiency is increasing or decreasing with the increase in the waste quantity, the process. Fine. So here, the biological technique, as you mentioned earlier, this process, since we are using microorganism, this process is essentially slow but pretty efficient. So here also you can see, using this, we can have 96% of copper, around 95% of zinc, 75% of nickel, and 75% of lead. Fine. And what we are getting is they can be achievable in 12 days. Fine. What we have also seen, if you increase the waste quantity, they will induce some kind of toxic effect and your efficiency will come down. Fine. So we need to look into that. So here also what we have seen is from this biometallurgical technique, whatever the metals are extracted, they can be further recovered using chemical precipitation, and one can use any other solvent extraction technique or whatever standardized techniques you will have. Fine. And we can see even the metal extraction efficiency, selective metal extraction efficiency are also high in this case as well. Fine. If you look at the mechanism wise, how this microorganism is acting on the solid particle or PCB particle, here we have grounded them. One mechanism, the bacteria, as their natural cycle, they produce a lot of exopolymeric substances. Fine. So once they excrete this, using these exopolymeric substances, they will bridge between this PCB particle and the bacterial cell. Fine. Now, what we mentioned that the media, what we provide 9K media, there we provide some kind of iron salt. So you have plenty of iron. Fine. Now, what bacteria does? One mechanism is what is calling it as direct mechanism. The bacteria is attaching with this PCB particle with exopolymeric substances, and then the bacteria is also working on this whatever ferrous iron you have in the media. So they are biologically oxidizing Fe2 plus to Fe3 plus. This Fe3 plus further, because whatever the metal you have in the PCB, they are in the ground state. Fine. So they are, once you have this Fe3 plus, this is again a strong oxidizing agent. What they are doing, they are knocking this ground state metal to M2 plus. That means they're bringing them to, or let us say this should be Mn plus. Okay. So they are essentially bringing them into ionic state, and thereby this is available in the liquid medium. So this is what we're calling it as, it's essentially the direct mechanism. And in this process, although I am not explaining in much detail, there are a lot of enzymes which will be acting here. Fine. Another thing is what you have the indirect mechanisms which will have, which with respect to the acid generation in the, because they are acidophilic microorganisms. So acid generation, what you have, they can also have the metal extractions from this PCB particle. So that what is known as the, because this conversion of Fe2 plus to Fe3 plus, you will also have this H plus generation. So this H plus indirectly can also extract metal from the PCB particle. So this is what is about the mechanism. Now what we have seen here in biometallurgical technique, even if you employ a mixed culture of bacteria, they are very much efficient. But what we are saying is that time requirement is, let us say, still 12 days. Fine. Now we wanted to bring down this time requirement. So what I have done, as you have mentioned, one motivation was to combine chemical leaching using safer materials along with this biometallurgical technique. So what we have done, what we have is Jugaad method, or what we use in day-to-day life. Okay. So what we've used, the biometallurgy, what we have explained. Apart from that, what we have added is lemon juice. Fine. And as you know, lemon juice contains a lot of citric acid, which is the organic acid. Fine. So pulverized printed circuit board, this mixed culture of bacteria, along with what we have added is a lemon juice. Fine. Which contains citric acid. And so thereby, what you have two actions. One is the biological action, another is the chemical action by the citric acid. And that's why this is known as hybrid biology. Fine. And this can be chemical process, can be anything. We have used citric acid, and I will also show some kind of enzyme can also be used here. So once we have this hybrid bioleaching, so here we can also recover them using chemical precipitation. So you can see here the result from this using the hybrid bioleaching, bacteria as well as the citric acid, what you have seen, around 98% of copper, 98% of zinc, 81% of lead, and 78% of nickel. Fine. But still, the time requirement is 12 days. So the efficiency has improved, but time requirement still remains with 12 days. Fine. So we wanted to further work upon this, how this metal extraction time requirement can be shortened. Based on this, what we have done is we have developed a two-step sequential hybrid bioleaching technique. Now let me explain. Initially, in the single step, what we used to do, we used to have a printed circuit board, the grounded particles, bacteria, and media we have added together in the reactor. Fine. And then we have got the metal extraction, and then followed by metal recovery by chemical precipitation. In the modification, what you have seen is the two-step sequential mode. The two-step, what you have done, as I have mentioned, as you can see here, is essentially you have Fe2 plus, which is present in the media. They are bacterially oxidized to Fe3 plus. Fine. And this Fe3 plus, as I have explained, is knocking down this metal to convert it to M2 plus, and then again it is Fe2 plus. This Fe2 plus again take part in this reaction. So thereby some cycle will go on here, and thereby continuously metal will be extracted from the printed circuit board. So here what we have seen is essentially if you have a lot of ferric content, that ferric content which is responsible for the metal extraction. Fine. So what we wanted to have, we first wanted to have the 9K median bacteria first we wanted to grow, so that in the media, whatever Fe2 plus you have had, they will be fully converted to Fe3 plus. So when you add printed circuit board, then all the Fe2 plus has already converted to Fe3 plus. So that together all the Fe3 plus can attack the metal present in the printed circuit board. Fine. So this what we meant to is the two-step, and thereby during this process you can achieve maximum growth of bacteria. They will be essentially this log phase, or they can be also the maximum production of the biological production of the iron. Fine. Now once you have this maximum growth, then we are in the bioreactor, we are getting this printed circuit board. So that's why we are calling it as two-step sequential approach, hybrid biology. Now once you have printed circuit board along with this dose, and then we are adding, let us say, lemon juice or the citric acid. Fine. So by doing this, what you have seen, so as you can see explained here in the schematic, you have this media and bacteria is added. So they are achieved the maximum growth, and also have this whatever iron present here, they are fully converted to Fe3 plus. And then once this is done, then we are adding printed circuit board and citric acid in the second step. By doing this, what you have seen, this Fe2 plus to Fe3 plus conversion, it takes only 60 hours. Fine. Followed by, once you add the printed circuit board, what we have seen, is by this method, this efficiency of similar efficiency or even better efficiency can be achieved only in 48 hours. So 60 hours and 48 hours together you have 108 hours. Fine. So that 108 hours you have shortened it from 12 days. Fine. So substantial improvement not only with respect to your process efficiency, but also with respect to the time requirement. Fine. So that what you mean to say is the two-step sequential hybrid bioleaching of metal from waste. Followed by, we wanted to also have similar hybrid technique. Typically, those are favorable in wastewater treatment. So there, people use bioleaching. Okay. So here, when you employ microorganism, it will lot of we need to properly maintain. But can we think of using their product as catalyst? So let us say if you use glucose oxidase as an enzyme or biocatalyst. So glucose oxidase as enzyme biocatalyst is typically used in let us say biofentanyl process in the wastewater treatment. Same process we have applied here in the e-waste management of the printed circuit board. So glucose oxidase, pulverized PCB, and then we have tried what is known as the enzymatic bioleaching. For the first time, we have shown that during this process, the hydroxyl radical which will generate, they will essentially partially degrade the polymer matrix or the PCB particle, whatever you have, the metal are embedded there. So that polymer matrix, they are essentially partially dissoluting them. And thereby, it is facilitating the whatever the metals are embedded in the PCB, they are essentially getting dissoluted in the liquid medium. Fine. So by doing this, what we have seen, we have in lesser period of time, also we have got similar kind of efficiency. So if you do not use directly microorganism, but you can also have, if you're using some kind of biocatalyst or enzyme, you can have a similar or improved efficiency and with shorter process duration. Now you will wonder that once you extract the metals, what about the printed circuit board or the residue? Fine. So we have tried to find it out that what is the residual metal content, and based on which what we have done is we have also performed the toxicity assessment both experimentally and also model wise. And what we have seen, if this side is the raw material, we have mentioned both human toxicity, carcinogenic and non-carcinogenic, as well as environmental toxicity. If you see, this is the raw printed circuit board, and upon providing this treatment, this printed circuit board or the residue, they have substantially come down. Now we are in a position, once the metal are extracted, this residue PCB or the PCB residues can safely be disposed in the landfill, or they can be also recycled. And we have also done that experiment or that study, that this can be also used in the as building material. Let us say you use them in the concrete or the masonry. Fine. So nothing is we are disposing them. Extraction, and then whatever residue you have, you can further reutilize in the construction sector as well. Now this process, enzymatic bioleaching, not only we have performed this, let us say, smaller studies, but also we have done scale-up studies. We have done, let us say, 5 liter and 2 liter studies, both in continuous the start tank reactor as well as the column reactor. Fine. And there we have also got the higher efficiency. Although from the batch study we have got reduced efficiency, but in the scale-up study, essentially the efficiency is on the higher side. So this process then is what you're saying is that this process can be scaled up further or can be taken up with proper pilot scale study. This can be scaled up to the industrial scale as well. So in a nutshell, if you look at all these techniques, whatever we have mentioned, mostly they are eco-friendly technique. And if you look at in the management sector or any organizations, you will have some kind of SWOT analysis. Let us say you have a strength, weakness, opportunities, and threats. Right? So far, whatever the techniques, metallurgical techniques we have mentioned, they are essentially looking at the integrated and holistic approach without creating any kind of secondary pollutions. So that's why you can consider them to be eco-friendly technique. And as far as possible, they will have simple operations, high efficiency, and also have low energy requirement, unlike the pyrometallurgy. So these are considered to be the strength. Fine. what are the weakness, and can we try further that weakness can be converted to our strength. So with respect to weakness, whatever you have is, let us say we need to use in the biological technique, we need to use commercial media or chemical. Right? Can we think of some kind of waste material which can be co-treated with printed circuit board, and they can provide or they can support the microorganism, or they can provide as the media. So we are also working in that direction, that to have some kind of co-treatment of printed circuit board along with some kind of other waste stream. Fine. Also, what we have seen is that the printed, if you increase the waste quantity in the reactor, efficiency is coming down. So this is also a weakness. So what we are also trying to look into this pulp density restriction, to alleviate this pulp density restriction. And then we are working further so that this weakness can be turned into the strength. Now, if you look at opportunities, by doing this, we are treating, though nowadays nothing is called waste, everything is resource. So we are doing waste treatment, and thereby we are trying to have resource recovery, and thereby we are, as we have explained in the beginning, we are essentially having take, make, use and not disposal model, but rather economic regenerative model. What we are saying is the take, make, use and then regenerate model. Fine. So it is providing biomining and circular economy for economic development. So those considered to be as opportunities. Threat wise, if you look at if you particularly look at the biological approach, they are susceptible to external factors sometimes. Okay, and the recovery of metals, we need to have even further, like we are using chemical precipitation. We can use many other techniques, so solvent extraction or other techniques, and can that be also made further efficient. So this is what we have in the SWOT analysis. So in a nutshell, if you look at this metallurgical technique, linear versus circular economy, and whatever we have demonstrated through our research or whatever we have so far discussed, whatever earlier used to have, you get these metals from mining or get the resource, then you manufacture, then as a consumer you purchase, then you use it. Once they are obsolete at the end of life, you dispose them into a landfill. So by doing this, what we used to happen is we are creating environmental pollution and wasting resource, and thereby we have a lot of loss of development. And what we are trying to transitioning from this linear model, what you have is the circular economy model, that you get mine it, then you manufacture it, then you purchase it, use it once it is end of life through various schemes as mandated in the waste management rules, as I mentioned, whether it's a take back system or through the collection centers or through the refund scheme. You collect it, and in using environmentally sound techniques, we need to recycle them so that these resources can be again reutilized for manufacturing of this. So thereby we can have transition from the linear to circular economy. Fine. So this is what you're saying is the metal recycling from waste, linear versus circular economy. And that transition is very much needed in order to achieve the sustainable development goals by 2030, even in the waste management. So I'll stop at this. And before I stop, it will be my duty to acknowledge the contribution of my student. Whatever research work I have presented here, it is because of my students' work. So it will be fair for me to acknowledge their contributions. Okay, and I thank you all for your patience for listening to me. I'll be happy to answer any question. Thank you.
Well, that's thank you very much for nice presentation.
Mic, please. Use the mic, please.
Our, as a regulatory body, our concern is that just as we have mentioned the different kinds of that metallurgical system that going to be for recovery of the metals that in the electronic waste. We should concern and focus on the dismantling parts on the very prior basis. Until unless we are not going to dismantle the components of the different components of electronic waste, it would not be possible to recycle the waste valuable materials from that.
Very correct.
So that we should take care for the dismantling. we have mentioned in the different process of the mining metallurgical process that the like the plastic and materials, all that will go to the. We are concerned with the printed circuit boards. Once we recover the plastic materials, we recover the iron ferrous metals. Our concern should be mainly for the non-ferrous metals, which is very toxic in nature, and that's why due to presence of this non-toxic metal like lead, arsenic, cadmium, etc., and mercury, these are considered as a hazardous waste, electronic waste. If that they will not be there, there will not be any problem to the electronic waste. So our concern is that how we will recover the non-ferrous metals that is valuable for us. We have mentioned, of course, very good kind of technology that you've given that, but our intention is that whether this kind of technology you have mentioned that can it be practicable to the field level or the industrial level, or do we have any analyze any that is the financial components, that is the economic viability of this kind of technology. If it is not economic viability, nobody will accept this kind of technology in the field.
Of course.
Only that will be limited to the laboratories. So I would request to that if you have any economic viability different with respect to the different kinds of mining of that non-ferrous metals, so that would be possible to accept in the field level. So I would like to request you give the proper any economic viability backgrounds you have done for that, and if there is any environmentally sound management techniques that approved by CPCB or Ministry of Environment Forest for the electronic waste, because the regulatory authority only go for the roadmap given by the Ministry or the CPCB. In that, suppose that hazardous waste, we have to guide it by the different kind of technology mentioned by the CPCB and Ministry of Environment Forest, and that we only allow the industrial sector to follow this kind of technology, and without following that kind of technology, we are not going to give any consent to establish a consent to operate to the industry. In the similar fashion, is there any environmentally sound management techniques approved by CPCB environmental? To the best of our knowledge, there is no so far. To the best of our knowledge, sir, there in India, there is no any recyclers or proper recyclers. They are only just dismantling the parts, and they are going to export that material to the foreign country for their recycling. We don't have any recycling in India, sir. So what is your opinion? Can this your technology can be implemented in our state or in India itself?
So thank you. You have posed a lot of questions. Okay, and I need to answer one by one. Okay. First is what you have mentioned is with respect to economic viability, and we have performed that viability, and then only based on these 4 elements. Forget about the precious metals and all this. Okay, and we are not talking about the details considering the inflation rate and interest. Okay, so if you have preliminary cost benefit analysis, which can give you the economic benefits. At the same time, I will also like to mention here is that you need to not only look into, since it is a business propositions, obviously when someone invest in there, will look for profit. Okay, but at the same time, we should not only concerned about only the economic aspect, that how much profit we are gaining, but at the same time, as I mentioned, that we also need to look into the environmental protection as well, like we have mentioned a lot of toxic metals and all this. Okay, so one aspect is it is economically viable, and at the same time, what you have is it can also lead to the environmental protection. Fine, and if you bring the rare earth metals, or if you bring the precious metals into the picture, and it will be obviously even more viable. Fine. So that is one part of your question. Answer to one part of your question. Second answer is with respect to the environmentally sound technology. Fine. And if you mention this environmental sound technology, CPCB or the US management rules, they have not mentioned any kind of technology. They have only said there is a physico-chemical or biological treatment techniques. Okay. But it is for our scientific community to look into which technology is good, which technology is bad. Fine, and one can justify this. And that's why I have mentioned the comparative assessment of pyrometallurgy, hydrometallurgy, and also the biometallurgical technique. Fine, and through our research, we are starting. We are progressing towards. Let us say earlier, the biometallurgy technique was efficient, but time requirement was more. Now we have even shortened that. And there are also challenges, as I mentioned in the SWOT analysis. We are also working towards that. Fine. And since you are asking for whether this will be implementable in the field or not, and for that, I would like to request, and I have also proposed to the Pollution Control Board that we can have some kind of pilot scale study. And if required, industry partner can be bring into here. Okay, we will be the technology partner. And there are, I've talked to few companies from Gujarat. They are also interested to invest here with respect to this. And if they get green signal from the Pollution Control Board, we can have a pilot scale. Okay, and there we can try. Fine. So without trying, whatever practice we are following in the country is you dismantle it or decide get this thing and then send somewhere. Fine. So that practice will continue forever. And you have something better than nothing. Fine. So that is one aspect. Now, with respect to your dismantling question, we are also working on in collaboration with a colleague at IIT Patna in Mechanical Engineering Department. We are not only working on, let us say, dismantling, but also we are trying to have, let us say, classify and sort them. Let's say you have a printed e-waste, you dismantle it, then you will have a glass, you will have a plastic waste, you have metallic waste, and also the printed circuit board. Can we have some technology, automated technology, which do not require manual intervention as such? Let us say you have robotic intervention. Can we have those kind of things that they can be segregated, dismantle and segregate into different waste? Fine. And that has been demonstrated for solid waste management. Particularly, I'm not talking about the mixed waste condition, but we are talking about the source segregated solid waste. So in terms of source segregated solid waste, the non-biodegradable fractions we have successfully demonstrated to sort them in metallic stream. We have sort them in glass, plastic stream. Right? So similar way, we are also working on e-waste part as well, dismantling and then sorting. So we are doing our bit as far as possible from the scientific or research community.
Thanks. One more question, please.
Yeah, please.
CFL that has been added in our schedule of the electronic waste management rules now. So CFL is now one of the electronic waste.
Yes.
Sir, we so far that CFL is not being collected by any organized sectors methods. People are just keeping in the house. Either they are giving in the solid waste management box. Actually, already urban local bodies have to have their own domestic hazardous waste sector system for collection of that, and they have to keep that for proper storage at a particular place to channelize into the TSDA facility. We don't have any TSDA facility. Still, the CFL bulk is not going to be managed anywhere. So, what are the waste techniques for the recovery of mercury from the recovery of mercury from the CFL bulks? Do you have any technology established so far?
There are techniques for dealing with mercury, and as you know, mercury is very hazardous, and you need to deal with properly. Fine. So there are techniques, but my laboratory or my research team is not particularly focusing on the mercury. Okay. So it will not be pertinent for me to comment upon. But there are techniques for recovery of the mercury.
Because, sir, of course, that regulation has come.
Yes.
If the CFL bulk has an electronic waste, it has to be collected by through domestic hazardous waste. It has to be collected by the electronic waste system by producer. But still, no mechanism has been developed so far for the CFLs for the recovery or its disposal system.
Similar way, I'm not particularly talking about this mercury part. But similar way, we have seen the CFL we have characterized also.
Okay. The other waste that is I have to agree with that.
Yeah, other metals can be extracted. Mercury, as we have not worked upon, I should not.
My concern was that considering the electronic waste, you considered 50 to 60, 55% like iron and steel structure, plastic waste, plastic material is 30%. Only 10 to 15% is that the non-ferrous metal is there. We are not going to be concerned with aluminum, which is that can be recyclable. But precious metal that is containing only 10 to 15% as a very toxic metal as a non-ferrous metal. So if that non-toxic metals are not being economically recovered, so ultimate solution is that we dispose that with some sort of biotechnology that we dispose. That earlier meeting, Chairman was there, and that some research scientists from the Motihari Central University was giving that we can dispose that the different kinds of bio methods
Mhm.
So if his economic viability is there, we can go ahead
Mhm.
with the for the field application of that. If it is not economic viability, there would not be any possible for recovery of that waste, and that ultimately our line of action will be only channelization for the disposal for that system.
Mhm.
But also not, because our natural resources, we cannot go for the further long period for the disposal system. We have to think
Absolutely.
about that. But the economic viability is very important.
Yes, yes.
Until unless we are not going to have the economic viability, no any research work can be implemented on the ground levels.
True. Very
Thank
true.
you. Thank you very much, sir.
Sir. Hi, sir.
Hello.
Yeah.
Yeah, Mr. ADV Metal, please go ahead, please.
Hi. I'm representing ADV Metal. We are an e-waste recycling company. We are India's one of the first e-waste recycling company.
Yeah.
We have collaborated with CSIR, NM, CSIO, and Bhaba recently. We have been involved in manufacturing of rare earths, as well as we are recovering, recycling lithium-ion batteries on a large scale.
Yes, yes.
So in rare earth, we have been working on neodymium oxide and fluoride right now. And
Okay.
we have customers in Japan and South Korea, and we are exporting our material. So my question regarding this technology, which sir was talking about in the entire session, regarding CU copper recovery, we have been working on development of copper oxide nanoparticles.
So this
can you,
once we extract in the liquid medium,
yes,
then you can play with it. You can have a lot of other. You can convert it to nanomaterial, and people are also doing it. Fine. The problem lies with respect to how to get from the solid matrix like printed circuit board to the liquid.
yeah, we are doing it from printed circuit boards only, sir. We are working on that agenda right now. So
Yes.
can your technology help us in moving towards that direction?
Could you please repeat once again the question?
So can your technology help us in moving towards copper oxide nanoparticles development direction? Because there's a huge demand in the market, and we are seeing we are developing copper oxide through PCBs. Like the first 3-4 steps are easy, but then going towards nanoparticle development is quite difficult.
We can surely work upon, and we can surely collaborate and work upon on that.
Sir, regarding CFL and tube lights, I would like to just make one short point on this also, that we have tied up with CSIO, and in India, we are the only ones. There's another recycler right now in India. They are in Haryana. So we have the technology for recovering phosphor and mercury from the CFL and tube lights. And we are collecting a lot of e-waste from Bihar as well right now. We are based in Chhattisgarh.
Excellent. And as you are mentioning also the lithium-ion batteries.
Yes, sir.
So in the lithium-ion batteries, we have also the technology, the same technology we have applied, and particularly we have worked upon the cobalt and nickel. Right? If you know cobalt and nickel, and we have also participated. If you know that every year Tata Steel, they come up with some kind of technological challenges.
Yes, sir.
So they have also this time initiated this particularly for the one segment was lithium-ion battery, recycling of lithium-ion battery. So in the lithium-ion batteries, you will see that nickel and cobalt they are present,
Yes.
but they can be extracted in the liquid medium. Once they are extracted in the liquid medium, the nickel and cobalt, they cannot be selectively separated because they have almost similar physicochemical properties. Okay. So we have also worked upon that how to selectively recover, apart from, because chemical precipitation will not work there, right? So using solvent extraction, and subsequently we have probably recovered nickel and cobalt selectively, and pretty with high efficiency around 95%. Fine.
With some of the reasons, and we are right now at the stage wherein we are selectively recovering cobalt and nickel selectively on a big scale with the help of reasons.
Yeah, please go ahead.
With the help of reasons, sir, we are doing it right now for selective separation of cobalt and nickel and lithium. In India, with whom we are working together, ion exchange. Yeah, they have developed a few resins with which we are working right now. So it is possible that selectively it is separated.
Yeah, it is very much possible.
For solvent extraction right now.
Yes, yes. We are also following that same. You develop. And what is your name of the company and your good name?
Sir, my name is Rahul Jha. and
Rahul
I-
Jha,
Yes, sir. And I belong to ADV Metal.
ADV Metal.
Yes.
Okay, so kindly send an email, then we will be in touch.
Yes, sir. Sure.
Thank you very much. The mobile number. Thank you very much. I will be happy to answer any question. Sir, you had one question.
Yeah, I was asking about the lifespan that you have considered for different gadgets.
Yeah.
Is that India level average or?
No, it's a global average.
Okay.
And if you see, we have also provided references. Okay, so the global average, and those are what is calling as typical values. Okay.
Let's take
Yeah.
outside questions.
So these are typical values, and this is for the coming now. Yeah.
Any more questions from
Sandeep.
Mr. Sandeep? Any questions from Mr. Sandeep or Ms. Anjali Sharma? Those who are participating virtually. If you don't have any questions, we can take questions from those who present physically here. So any questions from the participants here who are in this hall?
Yeah, please.
Yeah.
Sir, I have
Just to
some
go
question.
for the just different processes. You have given, can we go for the extraction of the nickel, cobalt, and other metals by using the only chemical analysis with formation of the complex compounds? Because the cobalt, nickels, other compounds forming, they're having their own characteristics to form the complex compounds. And based on that chemical characteristics, we can extract that metals from the formation of different kinds. Suppose that chromium hexavalent chromium and chromium plus 3. Once we are using in the some sort of system, the hexavalent chromium that is in the hydroxide form, it form plus 3 plus 6 form, in acidic condition plus 3 form. But once plus 3 form, we add magnesium oxide, again it's converted to Cr plus 3 form, and then the liberation of that the chromium sulfate etc. metal like that. So we can use different kinds of chemical reactions can be used, like you mentioned in the we have mentioned in the alkaline condition media in the biomining system. You mentioned that we can use the different kinds of reaction that is these the specific reactions for the metals which form the complex compounds like cobalt and nickel, which can be differed by the different complex compound by having the color system. So we can use that kind of methods for the complex formation types for extraction of metal from this kind of PCB and etc.
So that precisely one, if you look at the biopolymers or the organic acids, fine. Let us see, we have used DTP or there is chitosan. They are essentially having the chelating property. Okay, or if you look at also the citric acid, they can also have affinity for the metals. So that's why they have been chosen. Okay, one. So here the problem is two. One is you have a metals are embedded. So those are mounted component having some kind of mechanized dismantling system or this thing. Mounted component can be taken out, and the mounted component there the metals are concentrated. But the part of the metal which are embedded in the solid matrix. Okay, how to extract them? Okay, one possibility is that you grind them, and then whatever the metal embedded, you expose them to some kind of media that can be chemical, which there we are saying you use some kind of safer chemical, or you expose them to the microorganism or the biocatalyst. So from the solid matrix, you bring them into the liquid. Once they are in the liquid, then and there what you are saying, you to bring them in the liquid, you can have complex formation. So that particularly we are doing. Okay. Once they are in the liquid, so then from the liquid you need to recover them. Okay. You can have the metal oxides as chemical precipitation, and then Mr. Rahul Jha is pointing out that you can also convert them once they are in the liquid medium. You can convert them into the nanoparticles. Nowadays, nanoparticles have a lot of environmental applications and other applications as well. Fine. So there. So separation, one is the bringing them into the liquid, and then selective separation.
So, thank you very much. I have some basic questions.
Yeah. Okay.
We have prepared something, the per capita generation. So what is where we stand and really what is the per capita electronic waste, electrical waste generation in India? And
if you want to reduce, we have to apply 6R technology. How this passage can go for reduction? What is your bigger? Because you are with the education also, you are in the research also, and you are having a vision how to reduce this quantum in the long run. How we should proceed?
See, I do not think if your e-waste in near future it will come down. E-waste generation, because you cannot ask people to stop using the technology or technological advancement. Okay, so more and more these gadgets will come, people will try to use. More features will come. Okay, you will have, let us say, a smart TV, and then there will be new features, people will go for that. Okay, you cannot prevent people to have this smart techniques. Okay, the advancement of technique. The more these are used, so what will happen is obsolescence age will come down, or the obsolete period. Okay, and thereby more and more US generation will be there. Right? So US generation, I do not think it will come down. Only thing is that through awareness, we can have, let us say, judicial use, or not judicial, or rational use, or rational procurement of these gadgets. And then this choice is again to the individual consumers. Fine. So
I agree. Your point.
Yes. Second aspect is what I have not presented here. That the per capita US generation. Per capita US generation is with respect to, because the population wise we are very high, and US generation, if you look, we are third highest. Okay, so we are somewhere in between. Okay, but let us say if you look at the US and all this, okay, so US per capita US generation is more. Fine. Also, this per capita US generation or US generation as such is linked to whatever is also known as the per capita purchasing power.
Yes.
Okay.
Economic
well-being. Okay. So this per capita purchasing power is positively linked with your US generation. Particularly, may not be that much closely linked to the solid waste, but maybe very highly linked to the US generation.
Okay, if we know the per capita generation, then why we fail to have data for Bihar?
Because I'm not a data collection agency or this thing. Okay?
I'm just why Bihar was not there?
Bihar was not there in this thing in the ASSOCHAM report. What I've got from the newspaper, so that's why I've quoted. Okay, from the newspaper, from some minister or government source, we have got this event.
And once you don't know what is the generation,
yes,
the recyclers will not come.
Even Mr. Jha was also saying they are also getting US because they're ultimately going there.
So again, a transport cost. One hand we are talking about carbon neutral. Another time we are talking about the transportation of the materials from one state to another. So that how
conflicting interests are always there in the sector, especially comes to management of waste.
The floor is open for you all.
I'll be happy to answer any question.
We are
if you set up the industries.
So we conducted e-waste inventory in the state of Bihar for 5 cities. Patna, in 2013. So in Patna, we just identified a total of 10,259 tons in 2013, and we that as per inventorization and projected amount was the 38,450. 3 types is going to be increased by 2020. So a huge quantity of that waste generation is expected in also in state of Bihar, is like line of the other states, because people are more smart than the smartphones.
Yes, absolutely.
Just of 3 years, 4 years, when they are not only 2 years, they are changing their phones now. Not only limited to phones, the other computers, etc.
Yeah, absolutely.
So the quantity of waste, the per capita or waste generation, agar electronic waste we are, that is also good enough to have adverse impact on the environment. But only thing that we have to think upon that in the right manner for its proper management.
Yes,
if it is not being properly managed, then nothing will be happening in the because it's as it is electronic waste, it is not going to happen anymore unless you are not going to dismantle or
Yes.
recovery the metals from the inorganized sector. Or
Yeah. So the enforcement of the rules with the regulators,
so
and we are trying our best to have environmental sound techniques.
But also the producers are that also not mandated for that have EPR systems, but they have not come to the actual they are deciding the actual responsibility because they are EPR authorization and given by CPCB, no doubt. But we as state procurement board only concerned with the 4 stakeholders. That is the recycler, refurbisher, manufacturer, and that is the recycler, dismantler, refurbisher, or 4 stakeholders. And there is no any this kind of stakeholder instead of BR. So everyone is supposed to have connected with the CPCB, and we have to work on that guidelines of that EP authorization. We have to go for that. But until unless they are not going to have comply the provisions of the EP authorization, that will not be possible to manage the electronic waste. So we have to aware thing. We have tried our best to give the so many paper advertisements, so many booklets for the electronic waste, but still we are on the floor.
Yes. Another aspect is in some parts of the world, this has been seen, and then we are also getting data, is that because of the COVID thing during these 2-3 years, because everything was from home and then work from home, WFH. So there also you have a lot of electronic gadgets consumption. Okay. So there is also likely to have a spike in US generation because of the COVID effect. That is also a chance.
Yes.
So that's why US generation, as I think, is also.
Because you have shown you have the data after 2019.
Yeah.
After that, I was about to ask this question: what was the spike?
So that's why
because IT sector made us survive during COVID also, economy also, sustainability also, and the electronic gadget also. So what will be the spike? That was there will be spike. Okay, sir.
Any other question?
Sir, any of the floor is open for all, please.
Happy to answer. Thank you very much. Thank you very much.
Thank you so much for an enlightening lecture today. We enjoyed your presentation, sir. Rather, I learned a lot from your presentation today. What the e-waste actually constitutes, and its quantum of generation in different parts of the world, and especially in the country, in different states. And it's true that in Bihar, we don't have any dismantler or recycler here as of right now. But there are few entrepreneurs, they are in touch with us. They are interested in establishing their unit here. One in Rohtas and another one somewhere in Patna. So this is a new development for Bihar. And it's rightly said that it is not properly documented how much e-waste is being generated in the state. This is very something serious. And there is a reason for it. Actually, right now, as explained by our scientific advisor, as of now, we are concentrating more on the EPR by the manufacturers and the recyclers and the refurbishers. And when we say about refurbishment, yes, state government, not only the government in our country, but also throughout the world, refurbishment, reuse is being promoted. Recently, universal charger system for mobile phones is under discussion now. Also, sir, you explained about regulatory provisions. As of now, we have e-waste management rules 2016, which was amended in 2018, where EPR provision was inserted, extended producer responsibility. As of now, we have about 142 collection centers on behalf of different brands. But still, we have miles to go. And also, when we speak of e-waste, even the government authorities, the common people, they should be made aware of the ill effects of e-waste, especially which is related to heavy metals. And so you explained about different technologies available for recycling and recovery of valuable resources from the e-waste. That was an eye-opener for all of us. Definitely, sir, we'll also explore, and as mentioned by you, we will be happy and open to collaborate with IIT Patna and any entrepreneur who are interested in establishing this unit here on a pilot basis. Definitely, we'll also support you, sir, and any entrepreneur who's interested to come here in Bihar, because we don't, as of now, we don't have any dismantler or recycler. Also, sir, with the increasing automation in every sector in our daily life, electronic equipments, printed circuit boards are being used enormous ones. So definitely in the days to come, this e-waste is going to be a big problem. Also, all of us, we know and we are seeing in front of our eyes that a lot of e-vehicle is being promoted throughout the world. Today, we gone through the newspaper that California in US, they have banned gasoline vehicle in order to promote e-vehicles. So the future is for the e-vehicles, and Government of India and Ministry of Environment, Forest and Climate Change is also preparing a draft battery management rules. This is very much relevant for this time period now. So with these few words, I thank you profusely for accepting our invitation and for delivering a wonderful presentation today, sir.
2 hours.
2 hours, but it was very much interesting.
Very interesting.
Also, so I take this opportunity to thank you as a token of gratitude and respect on behalf of our Honorable Chairman, Bihar State Pollution Control Board, on my own behalf and on behalf of my colleagues here who are present here, and also on behalf of those who have attended virtually also. Sir, I present a small memento to you, sir.
Thank you.
Also, I take this opportunity to thank those who have participated virtually. Especially I thank Mr. Rahul Jha for giving an very useful information about what you are doing and what you are expecting from Bihar. It's good. We will be in touch with you after this lecture, and let's work out how we can come out with a unit here in Bihar if you are interested. Thank you so much. Thank you, Ms. Anjali Sharma. Thank you so much. Thank you, all of you. Have a nice day. Good day.